Alright, today we're going to look at static equilibrium. When we talk about static equilibrium, we're going to go over some terms, do a couple sample problems, at least you can see how the math works, and then you'll have the opportunity to do some problems on your own to make sure you have understanding. So, static equilibrium. When we talk about static means not moving. Actually, static equilibrium means you do not accelerate, which means total force must be 0. Total torque must be 0. So this is a specific situation that we can set up. So when we combine our forces, they equal mg. Okay? Force 1 plus force 2 will equal mg. So here's my example of this. So we have this little guy who's sitting on his plank. This lady is applying this force. This gentleman is applying this force. Now, since if this is our axis of rotation here, then this force is this distance, right, away from the rotation, and then this gentleman's boy is this distance away, all right, 3/4 the distance. But we can use information from that then, with torque being equal to 0, to find out pieces of information about this. Forces can be calculated for static equilibrium. Our forces, in this case, force 1 plus force 2, minus weight, which is going down, will equal 0. And we can find torque in all these different situations, okay? And I'll kind of go through the steps of how we got this, how I got these numbers here in a second. But just want you to see that we can use and gather all kinds of information from this. So, here we got this child of mass m being supported by his parents who exert a force of F1 and F2. We want to find the forces required to keep the plank in static equilibrium, okay? So here's a note that's given in the problem. We want to use the right end, so we want to use this end as the axis of rotation. Okay, so this is going to be our 0 point. Now, here's what we know. We know force 1 plus force 2 minus mg equals 0. Since this is our axis of rotation, we're going to make an equation. So we're going to make an equation just for force 1. We know that using torque, all right, force 1 times L, which is this total length, plus mg times its length, which is 1/4 L, is also equal to 0, because net torque is 0. Now, one thing to think about is our directions. Torque here and torque here are going in different directions, okay? So, we make this torque negative, and this torque will be positive because of the directions that they're going, okay? Now that we know that, we can start to do the math. So we can solve this. We know that the L's will cancel out because they're both on the same side, right? And so if we solve this for F1, we know F1 is equal to 1/4 mg. Okay, so F1 is equal to 1/4 mg. Knowing that, we slide this and replace it into here. We have 1/4 mg plus F2 minus mg equals 0. And when I move all my mg's over, I got negative mg divided by 1/4, and I get my force to be 3/4 mg. Now, when we talk about our forces, obviously both forces are going up, so they're both going to be positive in this case. And that's what we expect to see. What this also means, I guess, I can also add this point, is that the force that the mother is applying only is holding up 1/4 of the child's mass or weight, while the father is providing 3/4 of the carrying weight. So by shifting the weight, we can determine how much force is needed to lift the object up on this beam. Now, objects will balance at something called the center of mass. The center of mass is the point where an object can be balanced. Now, this is a pretty steep-looking equation. But if I want to find the center of mass for two objects, okay, I pick a point, wherever that is, and I multiply the mass of 1 times the distance away, plus the mass of 2 times the distance away from that point, and then divide it by the masses added together, and I can find the center of mass for these two objects. One thing you'll see in a situation, like look here in these situations, usually center of mass is located closer to the more massive objects. When we talk about center of mass, that's what we're looking at there. You may have made mobiles at some point in your life. In doing so, the goal was to get this thing to hang different objects, and you hang them at different distances away from each other based on where you pick your center of mass to be. So let's say we wanted to find the balance point of this mobile. The balance point is where torque, or net torque, is 0. Okay, so it's where net torque is 0. So right here, M1 GR1, that's this, mass times gravity times its distance, is equal to M2 GR2. Okay, and those two, since they're equal to 0, they should be equal to each other. And then of course we can get rid of G. It's on the same on both sides. So mass 1 R1 is equal to mass 2 R2, and we can use that to find a balance point at any time if we know all the information. So here's a mobile that's being produced, and this is just food group 1. And you can see the mobile. We know the masses of a lot of objects here. What we don't know is the mass of this object, and so we want to find that mass to make it perfectly balanced. We're going to assume that the strings and the rods that we're using have no mass. Otherwise, we have to include that mass when we do things. So with that, we want to solve. So the first step is, if this is M1, I'm going to take all of these masses here and make them M2. So M2 is going to be equal to the 0.2 plus 0.3 plus 0.72 plus 0.48. And when I add all those together, I get 1.70 kilograms. So 1.7 kilograms is what I get for the mass of all these objects. Why I did that is because in the end, this is the only rod that's important to find the mass of 1. And this end of the rod is going to hold up all of these masses. So all this other information, though important, I guess, to make themselves balance, not important for what we're trying to solve for. So now that we know that mass 2 is 1.72, now we go ahead and make our equation. M1R1 is equal to M2R2. M1 we don't know, but the radius is 31 centimeters. You can convert to meters. The key is that as long as both of these measurements are in the same units, you're good. We multiply that by M2, which is 1.7, and times my R2, which is 18 centimeters. And then you can see we just divide both sides by 31, and we get the mass of 1 to be 0.99 kilograms. So really quick way to find that missing mass using static equilibrium. All right, another thing is that if we hold up an object, we can pick something called the suspension point, and that's where we can hold the object so it will suspend itself. We can use the suspension point, though, to find the center of mass of an object. So here's a wooden replica of the continental United States. And what we see is we picked this line to hang it on, all right? And when we hung it on here, this map is just hanging on its straight up and down. So it's vertical up and down. But if we draw a straight line from the point and we hang it straight down, all right, we can find the center of mass will be along that point. So what we then do is take another point, in this case just turned it over, and hung it until it stood still. Once it stood still, we knew we had another point where the center of mass would be, and where these two lines intersect is the exact center of mass. So we can find the center of mass of an object if we can suspend it. So we suspend it, draw a line, suspend it on the other side, draw a line, and where those lines intersect, that's our center of mass. An example of a center of mass problem could be you get a croquet mallet, and you're holding it by a string, and you found the center of mass. So this thing is suspended in the horizontal. If we take this and cut it right here into two parts, right along the center of mass, so we have this part with the head and this part with the handle, which is the piece with the mass of the head, so right here, is the mass going to be greater than, less than, or equal to the mass of the other piece? Now, if you recall, something we mentioned is that the mass closest to the center of mass is more massive, which means the mallet's going to have more mass. And that's obviously something that we intuitively we know, but mathematically it does prove true also. So whatever the center of mass is closest to, that's the end that's going to have more mass.